Okay, so we're first going to take a look at the general problem here. Sorry about that. Where we don't know exactly what C of rho is, but we do know that d rho dt is 0, and then that C rho is going to be whatever it is, it's the velocity, right? So the fact that d rho dt is 0 is going to tell you that rho is constant. At least that is to say it's constant along its characteristic. Now we have to go ahead and solve the other one to find out what the characteristic is. In this case, C is not actually a constant. It's just going to be something that is dependent on rho, right? But what are we going to have then, since first of all, we have that rho is a constant and we know we have an initial condition. So we know that rho of xt is going to be that f of x naught. Okay, so now let's find the characteristic. Because it's whatever this function is, it's going to be a function of f of x naught, right? But it's dx dt. You're going to get that x is c of f of x naught t plus x naught, right? So this is a line, and it's going to be, but there are going to be lines of varying slope dependent on where you would start, dependent on f of x naught, basically. So I can just kind of think about this characteristic as being a bunch of different straight lines. Okay, we'll draw that in a minute here. And what we want to point out, though, is that along each characteristic, the traffic density, the rho, is going to be constant. And you have to then figure out which line you're on. So I'll just sort of visually graph this in some kind of way, where you've got x is that, it's a graph of x and t, right? So any particular different x naught starting point is going to give you a line of a different slope, right? Depending on, of course, whatever f of x naught is. So there's your xt. X naught would then be the point right there where the line hits the axis, of course. Okay, well, let's now move on to an example where we take a specific C rho. This is like a slightly easier one than that thing with the U max and the rho max and whatever, but the idea is going to be the same. So it's good to sort of look at this example, and look at this example, and then we're going to look at the other example with the traffic flow. So if we go ahead and we look at what our velocity is, we have got then that x is 2 rho t plus x naught. Fine. It's not terribly surprising, but now what we have to figure out, though, is what rho is. They gave us a specific rho to start out with, right? So what is that going to do? How are we going to work that out? So if x naught is greater than 0, then my value of rho is 4, and if x naught is less than 0, my value of rho is 3. Okay? So in my characteristic line, I can now solve it, rather than x being a function of the other, I'm going to solve it for x naught, right? Because everything's in terms of x naught right here. So along that line, x naught is what I want here, at equal x minus 2 rho t. That's the characteristic, so along that line, rho is a constant, right? So let's put that in, see what we have there. rho is a constant, rho of x naught, right? Where is it coming? Comment. Hold on a second. Rho of x, there we go. So it's going to be the same as rho of x naught, x and 0, or better yet, rho of x naught at 0, right? And then we're just going to put in what rho is. It's either 3 or 4. But now what I really want is I want to essentially get rid of the x naught, right? I want to put it in terms of x and t. And so using my equation for x naught, I can just put that in there. I'm going to get x minus 2 t less than 0, and it's 4 x minus 2 rho of x naught t greater than 0. Okay, but now I have to be a little bit careful though, because I have two possible values, right? If x naught is less than 0, then rho is 3, so that top part becomes x minus 6t is less than 0, and the other one is going to become x minus 8t is greater than 0. So what I have is I have a slope of 3 and a slope of 4, okay, dependent on where I am. But what about the part in the middle? Okay? So let's kind of graph this, sort of. It's not a great graph, but just to give us some idea of what's going on. I've got some slopes here. And all of those are now going parallel. And then I've got some, maybe look a little bit like better like that. There's some slopes here. And those are all parallel on the other side, right? But there's that part in between, okay? And that part in between, the point at which they meet there, that's going to be my x equals 0 point. And now I have to figure out what's going on in between there. So in between there, it's kind of weird to think about it, but really what this is called it's called an expansion wave, right? Because what's happening is that distance is increasing between the two characteristics there as time goes on. And so we have to figure out what is actually going to go on in between there, and what we can do that by looking at what happens. And the reason this happens is because there's an initial discontinuity in the rho, right? Rho has a jump. So that's why you see how this is basically the way the jump percolates essentially through time, right? And so what's going to happen, I can figure it out by going ahead and solving for what's going on there at x equals 0, right? So if x equals 0, I just put in x equals 0, and I solve, I get rho equals x over 2t, and that's what's going to happen there. I'm putting them in red just so that you can see them a little bit better, but those are going to fan out like that. So these are actually called fan-like characteristics. If you want, your book also has a different picture of rho, like a three-dimensional picture with x and t on the plane and then rho in the z direction. So that's interesting kind of to look at that picture as well to get the idea of what the expansion wave looks like. So next we're going to go on to the second example, which is the elementary traffic flow problem. So if you remember, we had figured out what that C row was under the elementary traffic flow assumptions in the previous video. Okay? And what we're going to do with this one is we're going to take an initial condition which models a red light turning green. Okay? So first of all, we had the assumptions as we had set them up before. And that gave us that C row. And then in terms of the red light turning green, of course, you can think about it at the red light turns green at x equals 0. So before x equals 0, you have row max, and after x equals 0, you have 0, meaning all the cars are at their maximum before the light turns, and then there's 0 on the other side of the light. Okay, so you can think about it that way. Now, the way I'm going to solve the problem is very much the same. Okay. I'm going to take dx dt because there's no q, right? We still have d rho dt being 0, so rho is going to be a constant. So I'm going to look at the dx dt, right? Which is now this function u max times 1 minus 2 rho over rho max. So it's a little bit more stuff in there. I mean, those are all constants except for the 2 rho, so that's pretty much the same except for the rho. But it's a little bit uglier. So that's why we sort of started with the previous example. In any case, I get the same idea. I get x equals that stuff times t plus x naught. Or I want to maybe write it, well, I'll write it in a minute then. If I put this down, I do want to write it. I want to write it as x naught first. Let's do it that way. That's a little bit easier to understand when then we put it into row. So x naught equals x minus the u max stuff, right? So this stuff. And now we're going to kind of figure out what that means when we put it into this row, right? Because what I have written down here is that rho is a constant, so I've got rho at xt is rho at x naught 0, so it's my initial condition. It's rho max for x naught less than 0 or 0 for x naught greater than 0. So now I want to do what I did before and stick all that stuff in. Again, it might be easier if we just erased this and sort of just looked at it step by step, because there's a lot of little constants to keep track of. So let's just look at it step by step and then put it in the answer in the end. So for x naught less than 0, I know that my rho is rho max. So if I'm going to substitute that into the equation for the characteristic, that star equation, I'm going to have x naught be x minus u max times 1 minus 2 rho max over rho max, right? So I'm stuffing that into there. So basically I've got x minus, plus, right? Wait, because it's, times minus 1. There you go. So it's going to be x plus u max t. And remember, that's all equal to x naught, right? Which was less than 0. So this guy is all going to be less than 0. Right? So that is going to be, going to tell me that first part, it's rho max when I've got x being, all right, I'm just going to rewrite it here so we can see it. X is less than minus u max t. Okay, fair enough. So that's that first part. I'll just throw it up there for the time being. Now for the second part, we're going to do the same thing. In the second part, I've got x not greater than 0. I'm going to again substitute it into my star equation, but now rho is equal to 0. So that's just going to give me x naught equal x minus u max t, right? And this time we have x naught greater than 0. So that whole bit is going to be greater than 0. So it's going to give me x greater than u max t. So kind of similar to what we had in the previous example, we now have a region, in this case between minus u max t and plus u max t, where we have to figure out what the information is, like what's going on in that middle part. And so what is really going on, we can solve for it the same way we had solved for it before, okay? So that's going to correspond to that x naught equals 0, right? So, sorry about that. So I put that in there. I'm going to get this, and I'm going to solve this for rho, like we did in the previous situation, previous problem. Now we're going to have that piece of information right there, what happens with rho. Okay, so I'm just going to solve this. Rho equals whatever it's going to equal, right? It's going to equal rho max over 2 times 1 minus x over u max t. Okay, so that I'm going to put that in. I'm going to actually collect it all now, all 3 of those, so that we know. All right, I just wanted to point out, how did I necessarily know that this corresponded to this region from minus u max to plus u max t? How did I know that that corresponded to x equals 0? Well, if you go back, you can kind of see that, again, that was my original jump in my original discontinuity in rho max. From rho max, rho was rho max to 0, right? That's where that original jump happened at x equals 0. Okay? So, wait, hold on, this one, that's not what I want to write. I want to write that one down in the next part. Yes, so we have the 2 pieces that we know of at the point of discontinuity, of original discontinuity of our initial condition. We're going to get this expansion wave kind of behavior that we also saw in the previous example. Okay, so that is consistent with what we've seen. And that's going to be in between those 2 characteristics. So let me write up the answer, and then we'll talk about a little bit what we all have together if I look at this. Okay. What really happens though is that your traffic light at some point turns green, right? So the cars can travel forward, but it takes time, right? It takes time for the information to propagate back. Not necessarily the time for the driver to see it, right? But for the driver to be able to move his car forward. So the information that the red light has turned green propagates backwards at the rate of minus u max. You have to, because we're assuming sort of that the car then will start moving at the rate u max, right? But you still have to wait until all the cars before you move, right? So there's that information propagation. So you have that sort of expansion wave.